Here is a question that stumps even experienced Kubernetes engineers. When you create a service in Kubernetes and access it by its cluster IP, where does that packet actually go? The answer lives deep in the Linux kernel, in a framework called netfilter, controlled by a tool called iptables, and manipulated by a component called kube-proxy. By the end of this video, you'll understand what happens at the kernel level when a packet hits a Kubernetes service. You'll write iptables rules from scratch, trace packets through netfilter hooks, and inspect the actual chains that kube-proxy creates. Let's demystify Kubernetes networking. Before we dive into the kernel, quick definitions for anyone new to Kubernetes. Service is a stable network endpoint in Kubernetes that load balances traffic across multiple pods. The cluster IP is virtual IP address assigned to a service that doesn't exist on any physical interface. NAT is the technique of changing packet source or destination IPs as they traverse the network stack. And pod is a container or group of containers. It is the basic unit that runs your application in Kubernetes. Don't worry if these concepts are still fuzzy. We're going to see them work at the kernel level. By the end of this video, you'll understand them better than most Kubernetes users who just run kubectl commands. Before containers and Kubernetes, iptables was primarily a firewall tool. System administrators used it to allow or plug traffic to servers. But when Docker emerged, iptables took on a new role. It is enabling container networking. And the evolution is very simple. First, netfilter framework merged into Linux kernel 2.4. Then iptables becomes the standard user space tool for configuring netfilter rules. Then Docker uses iptables for container port publishing and NAT. Then Kubernetes adopts iptables for services networking. And now we have different modes like IPVS for better performance and eBPF for line rate processing. Netfilter operates inside the kernel networking stack. It's not a separate firewall appliance, it's built into the packet processing pipeline. Every single packet traversing your system goes through these hooks. Whether it's pod-to-pod traffic, service traffic, or traffic leaving to the intranet. And netfilter is kernel framework, when iptables is user space tool to configure it. Understanding this isn't optional for Kubernetes work. When service connectivity fails, when network policies don't work as expected, when you see mysterious connection timeouts, you are debugging iptables rules and netfilter behavior. This is foundational infrastructure. And let's start where every packet starts, at the network interface entering the netfilter framework. The netfilter framework defines 5 hooks points in the kernel's network stack. Think of this as inspection stations where the kernel says, before I continue processing this packet, let me check if anyone wants to examine or modify it. Pre-routing hook, the very first hook. Packet just arrived on the network interface, the kernel hasn't made any routing decisions yet. This is where we intercept packets before deciding where they should go. Think of pre-routing as the reception desk. Packets just walk into the door and we can redirect them before they even check where they're supposed to go. And common use cases are port forwarding and DNAT. We change where packets are going before routing. Also, it can be connection tracking setup. We mark new connections for tracking and early packet classifications. We tag packets for special handling. Standard port traffic enters via WAF pairs and hits pre-routing, not output, because from the host perspective, it's traffic arriving on an interface, not locally generated traffic. Without pre-routing DNAT, packet arrives on service IP in Kubernetes, and routing lookup says that this IP is not my routing table, and then this packet being dropped. But with pre-routing DNAT, packet arrives on service IP, pre-routing changes it to Pod IP, and routing lookup says that this IP is reachable via, for example, CNI 0 breach, and this packet being forwarded to Pod. And we must change the destination before routing, otherwise the kernel makes the wrong decision. After pre-routing, the kernel performs a routing lookup. Critical question: is this packet destined for a local process, or should I forward it to another network? The kernel checks its routing table to answer who should handle this packet. And we have three possible outcomes. First is destination matches a local interface IP, so it is local delivery path and its input chain. If destination matches a route to another network, then it's forwarding path and forward chain. And if there is no route found, packet dropped with ICMP network unreachable. This routing decisions is the fork in the road. It determines whether packets hit input or forward. If the destination IP matches a local interface, the packet goes to input hook. This is the last checkpoint before packets reach local processes. After the routing decision determined that this packet is for me, input chain decides whether to actually allow it through. So input chain is firewall for local services. Think of input as a bouncer at a club. Routing decision says that you're on the guest list, so destination is local, but the bouncer still checks if you are actually allowed in. And common use cases are firewall rules for local services, for example, allow SSH from trusted IPs or block SSH. It can be rate limiting to prevent denial of service. It can be state-based filtering, and we can protect kubelet etcd APIs on Kubernetes nodes with these rules on input chain. And what traffic hits input? It can be HTTP requests to web server running on this host, SSH connections to this host, Kubernetes API server requests, kubelet API requests. And what traffic does not hit input is traffic being forwarded, for example, to container, it hits forward. Instead, traffic being forwarded to another network also hits forward, and locally generated traffic that uses output instead. So if you can connect to a service running on the host, you can check input chain rules. And we have different path for traffic. If routing says this packet is meant for somewhere else, it goes to forward hook. This is the firewall for routed traffic. When the host acts as a router between different networks, forward controls what's allowed to pass through. So forward chain is firewall for traffic passing through the host. But what happens at forward? Think of forward as a border checkpoint. The packet isn't staying here like an input, and it didn't originate here like an output. It's just passing through, and we decide if that allowed. And common use cases are container to intranet traffic, intranet to container traffic, pod to pod traffic across different nodes, VPN gateway scenarios, and it can be Kubernetes network policies, because it's implemented by CNI plugins in forward chain. And what traffic hits forward? For example, it can be container making HTTP requests to intranet, external client accessing container via port forwarding after DNAT and pre-routing, pod-to-pod traffic, and traffic routed between different interfaces. And what traffic does not hit forward? It can be traffic destined for the host itself, it uses input, traffic generated by the host itself uses output, and pure bridge forwarded traffic. It's L2 only unless BR netfilter is enabled. So we will talk about it later. And here we have critical detail, Docker's forward chain behavior. So when Docker starts, it enables IP forwarding at kernel level and then sets forward chain policy to drop. So it's default deny. Then it creates custom chains, Docker, Docker isolation and Docker user, and then adds its own accept rules for container traffic. But why the drop policy? Without it, your host would accidentally become an open router, forwarding any traffic between networks, and this is a security risk. And here we have a common problem. When you add a rule with iptables a forward, it appended to end, and by the time evaluation reaches your rule, packets were already accepted or dropped by Docker's rules, and your rule never runs. So solution is to use Docker user chain. And we have two requirements for container networking. First is kernel level, you need to enable IP forward, and second is iptables level, forward chain must have accept rules for container traffic. Miss either one and container networking silently fails. So if containers can't reach the internet or each other, check forward chain and IP forward setting. When a local application sends a response packet or when a local process initiates a connection, it enters the stack at output hook. This is the hook for packets generated by local processes, anything created by applications running on this host. So output chain is firewall or locally generated traffic. And what happens at output? Think of output as the exit security check for traffic leaving from local processes before it even gets routed. And common use cases are filtering outbound connections from the host. For example, prevent certain processes from making outbound connections or block access to specific domains or IPs. It can be Service ClusterIP interception, for example in Kubernetes. If a pod on this node accesses a service, kube-proxy intercepts in output and does DNAT. Also we can mark packets for quality of service or special routing, and we can use it for testing or debugging to log all outbound connections. And what traffic hits output? It can be web server running directly on host, sends HTTP response back to client, or process on host initiates SSH connection to another server, kubelet on host when queries Kubernetes API server, host network pods, Docker daemon making registry API calls, systemd services, cron jobs, or any process in host network namespace, but not standard pods. They use their own network namespace. And what traffic does not hit output? For example, standard pods hits PREROUTING instead via WAF interface, forwarded traffic, incoming traffic to local processes, or traffic arriving on any network interface. And in Kubernetes, this is where network namespaces become critical to understand. Whether traffic hits output or PREROUTING depends on the pod's network mode, and we have a few cases. So first case is most common, it's standard pods. Standard pods have their own network namespace connected to host via WAF pair. From the host kernel perspective, traffic from a standard pod looks like traffic arriving on a network interface. It's not locally generated. It came from a different network namespace through a WAF interface. Second case is less common. It is pods with host network true. They share the host's network namespace. So the packets from these pods hits output chain because they locally generated, because they have same namespace as host. And the third case is actual host processes. So it is processes running directly on the host. So for example, it can be kubelet, system daemons, or SSH sessions. And they also hits output chain because they locally generated. And this is why kube-proxy installs service rules in both chains. So pre-routing catches traffic from standard pods via WAF and external sources, and output catches traffic from host network pods and host processes. Output is also where locally generated packets get their first routing lookup. The kernel needs to know which interface this packet will leave from to properly handle things like source IP selection. After output, there is another routing decision to finalize the route. This is because output rules might have changed the packet destination, like the service to pod DNAT example. So both paths, forwarded packets from forward and local packets from output, now converge at the final hook. It is post-routing hook, the last checkpoint before packets leave the network interface. Routing is finalized, output interface is selected, and this is our final chance to modify packets. Think of post-routing as the departure gate at an airport. Your destination is set, routing done, your gate is assigned, interface selected, and this is the last security check before you board the plane, so packet leaves. And common use cases are SNAT and masquerade. We change source IP for outbound traffic. For example, container traffic appear as host IP. Private network appear as public gateway IP. Also, we can use it for source port translation or connection tracking and final packet marking before leaving the host. And why post-routing or SNAT? Because we need to know where the packet is going, which interface it's leaving from, and what the outgoing interface IP is. And all this information is only available after routing, which is why SNAT must happen in post-routing. And what traffic hits post-routing? Everything leaving the host. For example, forwarded traffic, locally generated traffic, response traffic, and new outbound connections. So let's take an example from Kubernetes. Container makes request to google.com, so pod sends a packet with the SRC of its own IP address and destination of Google's IP address. So routing sends this packet via ETH0 interface to the internet, and then we have forward chain with accept rules, and then this packet arrives at post routing. And there we have masquerade rule that translates our pod's IP address to host's public IP. Then the packet leaves, Google replies, host receives reply, and conntrack reverse NAT to pod's IP. So in this packet forwarded back to container. And there is Docker's typical masquerade rule. If packet is from containers and leaving via non-Docker interface, we will masquerade it. And we don't masquerade container to container traffic. This is the fundamental architecture. Every packet follows this flow. The hooks are fixed in the kernel. What we control with iptables are the rules that execute at each hook. Let me give you a simple way to remember this. If traffic to the host, it arrives, then goes to pre-routing, then to the input, and then to the local process. If traffic from the host, it goes from local process to output, then post-routing, and then leaves. But if the traffic goes through the host, it arrives, goes to pre-routing, to the forward, and then to post-routing. And after these three hooks, it will leave the host. iptables organizes rules into tables and chains. Tables group rules by purpose. Filter table is default table, contains rules for allowing or blocking traffic. Net table contains rules for network address translation. It changes source or destination IP ports. Mangle table contains rules for modifying packet headers. Row table contains rules for connection tracking exemptions. And security table contains rules for SE Linux packet labeling. The mangle table has a unique characteristic. It processes every single packet at every hook, regardless of whether any rules match. Other tables, especially NAT, are optimized to skip processing when no rules apply. This makes Mangle perfect for packet marking, header modification, observability and logging, and connection tracking metadata. Why we'll use Mangle for logging and demos? Because Mangle processes all packets. It's reliable for observability. The NAT table might skip packets that don't need NAT, causing log targets to be missed. Always use Mangle for logging or monitoring rules. And here is what makes this complex. At each hook, packets traverse multiple tables in a specific order. Why does NAT happen in pre-routing? Because we need to change the destination before routing. If a packet arrives for Service ClusterIP and we want to route it to Pod IP, we must change the destination before the kernel performs its routing lookup. Otherwise, the kernel would make the wrong routing decision. Between raw and Mangle tables, something critical happens: connection tracking. The conntrack kernel model sees every packet and maintains a state table. It tracks new, established, related, or invalid. This is how the kernel implements stateful firewalling. You write a rule allowing new connections, and established connections automatically work both directions. And critically for NAT, this is how return packets get automatically unnetted. So it is reverse NAT. So connection tracking enables stateful filtering and automatic reverse NAT. Within each chain, rules are evaluated sequentially top to bottom. Each rule has match criteria, protocol, source IP, destination port, interface, connection state, etc. and target and action, what to do if the packet matches. And we have common targets. It is accept, job, reject, log, DNAT, SNAT, masquerade. So I think it's clear. And here is the performance issue. Rule evaluation is ON. With 10,000 rules, every packet checks against all 10,000s until it finds a match or reaches the end. In large Kubernetes clusters, this becomes a real problem. Now that we understand the architecture, let's see NAT in action, because NAT is the foundation of Kubernetes Service networking. Network address translation comes in two flavors, and they operate at different hooks. First one is DNAT, it happens in pre-routing, it changes the destination IP or port before routing. So for example, Kubernetes Service receives packet, kube-proxy's iptables rule in pre-routing, change destination to Pod IP, now routing works correctly. Second one is source NAT, SNAT, it happens in post-routing, it changed the source IP or port after routing. So let's understand the fundamental problem SNAT solves. Containers get private IP addresses, and these addresses are non-routable on the public internet. Internet routes are configured to drop packets with these source IPs. So without SNAT, here is what would happen. For example, container sends a packet to google.com. So host routes packet to internet gateway, packet reaches Google server, and Google tries to reply to private IP. And we will have failure because Google's router doesn't know how to route this private IP. So even if by some miracle the packet reached your ISP, they will drop it because private IPs aren't valid on the public internet. With SNAT in post-routing, so for example, container sends packet to google.com, then this packet hits post-routing SNAT and it changes source to host public IP. So then packet reaches Google server with a routable source IP, Google replies to our host public IP, and this works. Then packet arrives at host and conntrack sees that this is a reply to connection via tracking. And then conntrack will do automatic reverse translation. And destination of our public IP address becomes a container IP. So and packet reaches container successfully. So SNAT makes private container IPs appear as the host public IP to the outside world. Masquerade is dynamic SNAT, special case of SNAT that automatically uses the IP of the outgoing interface, and it's perfect for hosts with dynamic IPs like DHCP or AWS instances. So with SNAT you specify the exec IP, it is faster, requires static IP, but Masquerade automatically uses outgoing interface IP. And this is why Masquerade has slightly higher overhead, because it looks up the interface IP for each packet. When iptables creates a DNAT rule, conntrack records the translation in its state table. For every packet in the connection, both the outbound and return packets are handled automatically. This is why you only need one DNAT rule. You don't write separate rules for return traffic. The conntrack entry looks like this. The first tuple is original, before DNAT, and second tuple is reply, with translation supplied. Theory is complete, now let's build this from scratch. Terminal time. Let's prove how packets flow through hooks by logging every stage. I'm going to set up login rules at each hook point, start a web server, make a request and watch the logs. First of all, we need to clean state, flush all existing rules. Now add login rules at each hook, watch the chain names and table names carefully. We're using the mangle table for logging because it processes all packets, unlike NAT, which only processes packets needing NAT. Remember from earlier, mangle is perfect for observability. First we will add pre-routing rules, then input, output, and post-routing. So now let's verify that rules are created. Now start a simple HTTP server and make a request to localhost and watch the kernel logs. You should see output like this, multiple entries per connection. If you don't see post-routing logs, it means you put the log rule in the NAT table instead of mangle table. The NAT table's post-routing only processes packets that match NAT rules. For pure observation, always use mangle table. It sees all packets at every hook. Also notice we didn't see forward chain. That's because this was localhost traffic. Routing decision sent it to input, not forward. But why does localhost traffic hit pre-routing? Locally generated packets normally don't traverse pre-routing, they start at output, but loopback traffic makes a round trip, output to post-routing, then sent to LO interface, received back on LO interface, then pre-routing, and then input. When the packet is received back on the loopback interface, it's treated as an incoming packet, so it hits pre-routing. This is why you see pre-routing triggered even though the traffic is locally generated. Let's prove the forward path exists. We will add forward logging, not triggered by localhost, and verify forward wasn't triggered by our localhost requests. To trigger forward, we would need traffic routed between different interfaces, like container to external network. We'll see that next. And finally make a cleanup, stop the Python server before next demo. For this demo you need two VMs in the same network, both can communicate with each other. And first ensure BR netfilter model is loaded. By default, Linux bridges operate at layer 2, MAC addresses, and don't pass traffic through iptables. This means packets bridged through Docker 0 will bypass all our NAT rules. BR netfilter model enables bridge netfilter, makes bridged packets traverse iptable chains. Without this, packets bridged on Docker 0 will skip pre-routing, forward and post-routing, and our DNAT rules wouldn't apply. And this is why Docker and Kubernetes require this model. You're literally telling the kernel, even though Docker 0 is a bridge, still run packets through the iptables firewall. Now let's implement what Kubernetes kube-proxy does. DNAT for service to pod forwarding. We'll use Docker to simulate this, and we will test two different traffic paths to understand when forward chain matters. First, we will start nginx container and don't publish ports with p flag. Now we'll create DNAT rules, first for pre-routing and second for output. But why do we need both? Pre-routing catches traffic arriving on network interfaces from other machines or from pods via WAF, and output catches traffic from local processes on this host. And this is exactly why kube-proxy installs service rules in both chains. Before we add masquerade rules, let's understand when and why they are needed. First, let's trace what happens without masquerade in our VM2 to container scenario. Inbound path will be like this. VM2 sends a packet to VM1, prerouting DNAT transforms destination of VM1 to container IP address, conntrack creates entry, triggering disconnection, then container receives the packet, and return path container replies to VM2 destination with SRC of its own IP address, and conntrack recognizes this as a reply packet and automatically reverse DNAT, and packet becomes with SRC of VM1 and destination to VM2, and VM2 receives correct reply. For this simple scenario, DNAT alone might actually work. Conntrack automatically handles DNAT reversal on reply packets. So when is masquerade critical? Container to internet traffic. Without masquerade, the container's private IP would appear on the public internet. External servers have no route back to private IPs, so connection will fail. Next one is reverse path filtering. If RP filter is enabled, the kernel drops packets where the source IP wouldn't roll back out the same interface. Next is production multi-node scenarios. Kubernetes node port always uses masquerade to ensure replies route correctly through the node that received the original request, even with complex routing topologies. And the last one is routing predictability. By masquerading to the local bridge IP, we guarantee the container sees traffic from its default gateway. For our demo, we'll use masquerade following production best practices, even though DNAT alone might work in the simple 2VM scenario. So, we will add masquerade rules. First one is Docker's default masquerade container to intranet, and second one is masquerade for external traffic to containers. And we need two masquerade rules for bidirectional net. Rule 1 matches traffic from containers going to external networks, masquerades container IPs to appear as host IP. And second rule matches traffic to containers from external source, masquerades external client IPs so containers can route replies back. And also, these rules prevent masquerading container to container traffic on the same bridge. Let's analyze which rule will match when VM2 sends traffic to our container. So first rule does not match, but rule 2 matches and masquerade applied. So rule 2 changed SRC from VM IP to Docker 0 bridge IP, and this is critical. Rule 1 is for container outbound traffic. Rule 2 is for external inbound traffic. The conditions are specifically designed to distinguish these two traffic directions. So let's test from localhost. Test DNAT via Docker 0 IP from this host. It works. Now let's check the forward chain counters. And it shows 0 packets in forward chain. This is critical. Locally originated traffic bypassed forward entirely. Let's trace the packet path for our requests from the host. This traffic was locally originated by the host itself. It went through the output chain, not pre-routing. Forward chain only applies to traffic that arrives on one interface, needs to be forwarded out a different interface, and is not destined for the local host. Our curl traffic originated locally on the host, so it followed the output path. The routing decision determined it should go to Docker 0, and it was delivered directly, no forwarding required. And why external VM traffic will traverse forward? When VM2 sends traffic that VM1 must forward to a container, packet arrives on ENP0S1 interface, goes through pre-routing chain, then routing decision that this packet must exit via Docker 0 interface. This is forwarding between interfaces. Forward chain is traversed. Then post-routing before leaving to Docker 0. And this is the fundamental rule. Forward chain is for packets being forwarded between interfaces. Output chain is for packets originated by the local host. Our test used output, so forward was never in the path. So now we will make requests from external VM. And this is expected failure. Let's diagnose what happened on VM1. And on VM1 we will check forward counters. Forward counters are now non-zero. External traffic does hit forward. So now we will insert at position 1 before Docker's chain login rule and check kernel logs for forward chain traversal. So what's happening? External traffic crosses interfaces ENP0S1 and Docker 0, so it must traverse forward chain. So let's look at Docker's built-in chains. We see Docker chain with drop rule. So Docker security model blocks external access to containers unless we published it with a P flag. This drop rule says if traffic is coming from any interface other than Docker 0 and going to Docker 0, drop it. We need to use Docker user chain for our custom rules. And we will add rule to Docker user chain to allow external access. Docker user chain is for user-defined rules. It's evaluated before Docker's built-in drop rule, so our accept rule takes precedence. First, let's check conntrack state before the request on VM1. Now send the request from VM2. Perfect. Let's verify the complete flow on VM1. We see that forward counters incrementing an established connection in conntrack, and connection tracking is the memory of NAT. And let's examine that conntrack entry carefully. This is a secret sauce that makes bidirectional NAT work. So first tuple is original direction. This is one VM2 sent, the original addressing. And second tuple is reply direction. This is what the container sees, the transform addressing after DNAT plus masquerade. The kernel stores the reverse for replies. Containers SRC becomes our destination. The assured flag means connection has seen traffic in both directions. It's established. So why this matters? When the container sends a reply, netfilter looks up this conntrack entry and automatically reverses the masquerade and reverses the DNAT. This is stateful NAT. We only need rules for the forward direction. Return traffic is automatically handled by conntrack's memory of the connection. Before we trace the full packet path, let's verify the routing decisions. See how kernel routes to container IP and see how kernel routes back to VM2. These routing decisions happen after DNAT and after masquerade reversal. They are what determine that packets must cross interfaces, triggering forward chain traversal. Now let's trace the complete packet flow that just succeeded. And we can check NAT table with packet counters. This is how you debug IP tables. Check packet counters to see which rules are actually being hit. Now for the moment of truth. Let's see what Kubernetes kube-proxy actually creates. I'm using a Minikube cluster for this demo, but production Kubernetes nodes look identical. First, let's deploy a simple application with multiple replicas and expose it as a service. Let's check the service details to get a cluster IP, and that IP doesn't exist on any interface. Let's find it in IP tables on the Minikube node. I will access the node with Docker exec because Minikube nodes are Docker containers, and inside the node search for our service IP. Kube-proxy created a custom chain called kube-svc hash. Let's explore the full structure. We'll see the entry point where service traffic is intercepted. The kube services chain is jumped to from two places: pre-routing for external traffic and output for pod local traffic. Every service gets one entry here that redirects to its specific kube-svc chain. Now let's see the load balancing logic. Let's inspect our services chain. This is brilliant probabilistic load balancing. First endpoint gets a 33% chance, 1 out of 3. If that doesn't match, second endpoint gets a 50% chance, 1 out of remaining 2. If that doesn't match, third endpoint is guaranteed. Now let's see what kube-sap chains do. Pick one endpoint chain. The actional DNAT that changed the service cluster IP to a pod IP. This is exactly what we did manually in the previous demo. Let's count how many roles exist. Just 18 chains for a tiny cluster with a few services. In a production cluster with 1,000 of services and 1,000 of pods, this could be a lot of rules. Now you understand why iptables mode doesn't scale well, because every packet traverses this chain structure. You now know exactly how Kubernetes services work under the hood. When service connectivity fails in production, you know where to look. You can trace these chains like kube services, kube-svc, kube-sap to find the problem. In clusters with more than 1,000 services, iptables mode cause measurable latency increase. And the solution is to migrate to IPVS mode or eBPF based solutions like Cilium. So let's review what you now understand. First, the netfilter framework. It provides 5 hooks in the kernel packets processing pipeline. It is pre-routing, input, forward, output, post-routing. Every packet traverses these hooks. iptables is the user space tool that configures rules at these hooks, organized into tables like filter, NAT, mangle, row, and chains. DNAT happens in pre-routing, before routing decisions, changing destinations IPs. This is how Service ClusterIPs gets translated to Pod IPs. SNAT happens in post-routing, after routing, changing source IPs. This is how containers masquerade behind the host IP. Kube-proxy in iptables mode creates different chains: kube services, entry point, kube-svc, per service, and kube-sap per endpoint with DNAT. Probabilistic load balancing distributes traffic across pods. Connection tracking maintains state for every flow, enabling stateful filtering and automatic reverse NAT. When the table fills up, connectivity breaks. When service connectivity fails, you now know the investigation path. Verify kube-proxy is running, check kube services chain for service entry, follow chain jumps to kube-SVC and kube-SEP chains, verify DNAT targets, point to live pod IPs, check conntrack table isn't exhausted, verify forward chain allows traffic. This isn't magic anymore. It's traceable, debuggable kernel mechanics